So the second lecture is about Erdős-Ko-Rado properties of graphs. So the floor is yours.
Thank you very much for the introduction, and thank you very much everyone for the interest. The second lecture is entitled EKR properties of graphs, and let us recall the background on the Erdős-Ko-Rado theorem. The Erdős-Ko-Rado theorem, one of the fundamental results in combinatorics, provides information about systems of intersecting sets. A family A of subsets of a ground set, it might as well be the set from 1 to n, is intersecting if any two sets in A have at least one point in common. More generally, a family A of subsets is T-intersecting if any two elements of A have at least T points in common. And in 1961, Erdős-Ko-Rado proved the following theorem. Let K and N be integers with the property that N is greater or equal to K. If A is an intersecting family of K subsets of the set from 1 to n, then the size of A is at most the binomial coefficient n-1 choose k-1. Moreover, if n is strictly greater than to k, equality holds if and only if A consists of all the k subsets that contain a given point from the ground set. This theorem has two parts, a bound and a characterization of families that meet the bound. One reason this theorem is so important is that it has many interesting extensions. To address this, we first translate it to a question in graph theory. The Kneze graph K of nk has all k subsets of the set from 1 to n as its vertices, and two k subsets are adjacent if they are disjoint. We assume that n is greater or equal to k to avoid trivialities. Then an intersecting family of k subsets is a co-clique in the Kneze graph, and we see that the Erdős-Ko-Rado theorem characterizes the co-cliques of maximum size in the Kneze graph. So we can seek to extend the EKR theorem by replacing the Kneze graphs by other interesting families of graphs. There is a second class of extensions of the Erdős-Ko-Rado theorem. In their paper, they proved the following. Let n, k, and t be positive integers with the property that t is between 0 and k inclusive. There exists a function f of k and t such that if n is greater or equal to the value f of kt and A is a t-intersecting family of k subsets of the set from 1 to n, then the size of S is at most the binomial coefficient n minus t choose k minus t. Moreover, equality holds if and only if A consists of the k subsets that contain a specified t subset of the set from 1 to n. There are graph theoretic analogs of this question too. In place of the Kneze graphs, we use the Johnson graph J of nk. The vertices of J of nk are the k subsets of the set from 1 to n, but now two k subsets are adjacent if they have exactly k minus 1 points in common. Again, we assume that n is greater or equal to k. The graph J of nk has diameter k, and thus two k subsets are adjacent in k of nk if and only if they are at maximum possible distance in J of nk. Define the width of a subset of the vertices of a graph to be the maximum distance between two vertices in the subset. Then our first version of the EKR theorem characterizes the subsets of maximum size in the Johnson graph J of nk with k minus 1, and the second version characterizes the subsets of maximum size with width k minus t. All known analogues of the Erdős-Ko-Rado theorem for T intersecting sets can be stated naturally as characterizations of subsets of width d minus t in a graph of diameter d. However, such theorems have only been proved in cases where the distance graphs form an association scheme, that is, they fit together in a particularly nice way. To give one example, we can replace k subsets of the set from 1 to n by subspaces of dimension k over a vector space of dimension n over the finite field of order q. It is easy to find small intersecting families. The basic problem is to decide how large they can be and to describe the structure of the families that meet whatever bound we can derive. The second version of the theorem is clearly more general than the first one, but has the weakness that its conclusion holds only if n is greater than some unspecified lower bound. We call a collection of subsets of the set from 1 to n a set system with underlying set from 1 to n if the subsets all have size k. If the subsets all have size k, we refer to it as a k set system. The easiest way to build a T intersecting k set system on an n set is to simply take all k subsets that contain a fixed T set. Clearly, such a system has size the binomial coefficient n minus t choose k minus t. We call a set system of this type a canonical T intersecting family. The lower bound on n in theorem 2 is necessary because when n is not large enough, an intersecting family of maximal size need not be canonical. Much work was devoted to determining the precise value of f of nk needed. Examples show that we need n at least t plus 1 multiplied by k minus t plus 1 for the bound to hold. And in 1978, Frankel proved that these constraints sufficed when t was large enough. In 1984, Wilson proved that the bound in the EKR theorem holds if n is at least t plus 1 multiplied by k minus t plus 1, and the characterization holds provided that n is strictly greater than this bound. In 1997, Alswede and Khachaturian determined the largest T intersection k set systems on an n set for all values of n. The result of this work is that for each choice of n, k, and t, we know that maximum size of the T intersection families, and we know the structure of the families that reach this size. Somehow the question was completely solved, and let us discuss further investigations of this question. Erdős-Ko and Rado conjectured that the largest one intersecting system that was not a subset of the canonical intersecting set system is the set of all k subsets that contain at least 2 elements from a fixed set of 3 elements. It turns out that this conjecture is not true. The actual maximum sets were given by Hilton and Milner. Hilton and Milner proved that the largest intersecting system that is not a subset of a canonical intersecting system can be constructed as follows. Let F0 be the set system of all K subsets that contain the element 1, and let A be the set consisting of consecutive elements 2, 3, so on, K plus 1. Define F prime to be the system of all the sets of F0 that intersect A together with the set A. This system is intersecting and has size n-1, choose k-1, minus n-k-1, choose k-1 plus 1. The next result is shown is known as the Hilton-Millner theorem. Let k and n be positive integers with the property that k is greater or equal to 2 and less or equal to n over 2. Let A be an intersecting k set system on an n set such that the intersection of all the sets in A calligraphic is empty. Then the size of A is at most the number we discussed on the previous slide, n-1 choose k-1 minus n-k-1 choose k-1 plus 1. Moreover, for k greater, strictly greater than 3, equality holds if and only if A is isomorphic to the system of all sets in F0 that intersect the set 2, 3, so on, k plus 1 together with the set this set itself 2, 3, so on, k plus 1. For k equals 3, there are two non-isomorphic systems that meet this bound, the one described above and one more. In this mini course, we consider the first way to extend the EKR theorem. In order to do this, we need to define the notion of intersecting for the vertices of the graphs we consider. Once we have done this, we can define the notion of canonical intersecting families in these graphs. In this lecture, we consider two important families of strongly regular graphs for which the notion of canonical intersecting families, more precisely canonical cliques, is well defined. The first one is family of block graphs of orthogonal arrays, including Paley graphs of square order, and this would be an extension of our previous lecture, the extension of the discussion in our previous lecture. And the second family is the family of block graphs of 2NM1 designs. Given any graph X for which we can describe its canonical cliques, that is typically cliques with large size and simple structure, we can ask whether X has any of the following three related Erdős-Ko-Rado properties. EKR property, the clique number of X equals the size of canonical cliques. EKR-module property, the characteristic vector of each maximum clique in X is a Q-linear combination of characteristic vectors of canonical cliques in X. And strict-EKR property, each maximum clique in X is a canonical clique. Given a graph X for which an analog of the Erdős-Ko-Rado theorem is obtained, it is natural to ask whether an analog of the Hilton-Millner theorem can be established. Such a result is also called a stability result, since this shows what are second largest maximal with respect to inclusion cliques in these graphs. The classical Erdős-Ko-Rado theorem classified maximum intersecting families of k-element subsets of the set 1, 2, so on n when n is greater or equal to 2k plus 1. Since then, EKR type results refer to understanding maximum intersecting families in a broader context and more generally classifying extremal configurations in other domains. The book by Gotzel and Marr, Erdős-Ko-Rado Theorems, Algebraic Approaches, provides an excellent survey on the modern algebraic approaches to proving EKR type results for permutations, set systems, orthogonal arrays, and so on. And let us start our discussion of two particular families of graphs. The first one is the block graphs of orthogonal arrays, and let us recall the basic definitions. An orthogonal array OA of Mn is an m times n squared array with entries from an n-element set T with the property that the columns of any 2 times n squared subarray consist of all n squared possible pairs. The block graph of an orthogonal array OA Mn, denoted x with index OA of Mn, is defined to be the graph whose vertices are columns of the orthogonal array, where two columns are adjacent if there exists a row in which they have the same entry. Let S with indices r and I be the set of columns of an orthogonal array OA of Mn that have the entry I in row R. These sets are obviously cliques, and since each element of the n-element set T occurs exactly n times in each row, the size of S with indices r and I is n for all I and R. These cliques are called the canonical cliques in the block graph X with index OA Mn. So we use for the notion of intersecting, we use the property for two columns to share some symbol in some row. So it's quite natural. A simple combinatorial argument shows that the block graph of an orthogonal array is strongly regular. Moreover, by the third bound, a clique in such a graph, in a graph X with index OA of Mn, has size at most n, and the canonical cliques show the tightness of this bound. If we view columns of an orthogonal array that have the same entry in the same row as intersecting columns, then we can view the third bound as the bound in the Erdős-Ko-Rado theorem for intersecting columns of an orthogonal array. And the question is, under what conditions will all cliques of size n in the graph X with index OA Mn be canonical? The following answer can be viewed as the uniqueness part of the Erdős-Ko-Rado theorem. Let X with index OA of Mn be the block graph of an orthogonal array OA of Mn with the property that n is strictly greater than m-1 squared. Then X has the strict EKR property. The only maximum cliques in X are the columns that have entry I in row R for some I between 1 and n inclusive, and some R between 1 and m inclusive. This is equivalent to saying that the largest set of intersecting columns in an orthogonal array is the set of all columns that have the same entry in some row. And these sets are the only maximum intersecting sets. Let us formulate some open problems that appear in the book by Gotzel and Marr. Problem 1, find a characterization of the orthogonal arrays based only on the parameters of the array for which all the maximum cliques in the orthogonal array graph, that is in the block graph of this array, are canonical cliques. Problem 2, assume that OA of M and m-1 squared is an orthogonal array, and its orthogonal array graph has non-canonical cliques of size m-1 squared. Do these non-canonical cliques form subarrays? The book provides an example of non-canonical cliques in the block graph of an orthogonal array that form subarrays. In lecture 4, we discuss a subfamily of affine polar graphs that can be viewed as block graphs of orthogonal arrays containing non-canonical cliques having subarray structure. And a more general problem, determining all the maximum cliques in the block graphs for any orthogonal array. Let us discuss a family recently, a family that was recently called Paiser type graphs. Let Q be a prime power and let S be a subset of the multiplicative group of the finite field of order Q squared. Let S be a union of M cosets of the multiplicative group of the subfield in the multiplicative group of the bigger field, such that FQ star itself is included in S. That is, S can be written as a union of C1 FQ star, union C2 FQ star, so on, CM FQ star. Then the Kelly graph on the additive group of the finite field of order Q squared with generating set S is said to be a Paiser type graph of type M and Q. A clique in X is called a canonical clique if it is the image of the subfield FQ under an affine transformation. A Paiser type graph of type MQ can be viewed as a graph on the points of the affine geometry HG to Q, with 2 points being adjacent whenever the line through these points belongs to one of M prescribed parallel classes of lines. Paiser type graphs are equivalent to the block graphs of orthogonal arrays obtained from the parallel classes of the affine plane HG to Q. Another way to look at Paiser type graphs is to consider them as fusions of certain amorphic cyclotomic association schemes. Let us discuss how the class of Paiser type graphs intersects with some well-known infinite families of graphs defined on finite fields. So Paley graphs of square order, we discussed in the first lecture, are Paiser type graphs. Paiser graphs P star of Q squared, where Q is congruent to 3 modulo 4, are Paiser type graphs, but not all Paiser graphs are Paiser type graphs. Generalized Paley graphs GP of Q squared D, where D divides Q plus 1 and D is greater than 1, are Paiser type graphs, but not all generalized Paley graphs are Paiser type graphs. And also generalized Paiser graphs GP star of Q squared D, where D divides Q plus 1 and D is even, are Paiser type graphs, but not all generalized Paiser graphs are Paiser type graphs. Let us give a definition of one more notion. A vector in the vector space of dimension n over the real field is balanced if it's orthogonal to all one's vector denoted by one bold. If Vs is the characteristic vector of a subset S, of the set V, then we say that Vs minus the scalar, the size of S over the size of V multiplied by the vector 1 is the balanced characteristic vector of S. Any clique of size q in P of q squared is a Delsart clique. So now we discuss a question on Paley graphs of square order posed by Gotzel and Marr. Any clique of size q in the Paley graph of q squared, of order q squared, is a Delsart clique, and so its balanced characteristic vector lies in an eigenspace, in the eigenspace corresponding to the eigenvalue minus 1 plus q over 2. In section 5.9 of the book, Gotzel and Marr presented a possible alternate proof of Blokhuis result, and this possible proof relies on the following problems. First, show that this eigenspace corresponding to the eigenvalue minus 1 plus q over 2 is spanned by the balanced characteristic vectors of the canonical cliques. In our recent work with co-authors, we showed that solving problem 4 is equivalent to establishing the EKR-module property for Paley graphs of square order, and we did this in a combinatorial way for all block graphs of orthogonal arrays, including Peyser type graphs, and in particular including Paley graphs of square order. But we were not able to make the second step. It is still an open problem. Prove that the only balanced characteristic vectors of sets of size q in the corresponding eigenspace of the Paley graph of square order are the balanced characteristic vectors of the canonical cliques. In general, the module method, see a paper, for example, by Ahmadi and Marr, refers to the strategy of proving that a graph X satisfies the strict EKR property in two steps. First, show that X satisfies the EKR module property, and second, show that EKR module property implies the strict EKR property. As an example of the module method, this paper provides a sufficient condition for the second step above for two transitive permutation groups. Further, we list another recent results related to EKR properties of Peyser type graphs. The following theorem shows that all maximum cliques in Peyser type graphs of type MQ, where M is at most q plus 1 over 2, the total number of co-sets is q plus 1, and they correspond to slopes or directions in the affine plane. And if we consider Peyser type graphs such that at most half of the slopes involved in the adjacency relation, then all maximum cliques, even non-canonical ones, have nice algebraic structure. Let X be a Peyser type graph of type MQ, where Q is a power of an odd prime P, and M is at most q plus 1 over 2, then any maximum clique in X containing 0 is an FP subspace of the finite field FQ squared. It is a good open problem to give symmetric constructions of Peyser type graphs with M strictly greater than q plus 1 over 2 in such a way that these graphs have non-canonical cliques. So it's interesting both to give symmetric constructions for graphs and for their non-canonical cliques. The stability of canonical cliques in Paizer-type graphs has also been studied. For simplicity, we say that a Paizer-type graph X with order Q squared has the property St of K if each clique in X with size at least Q minus K is contained in a canonical clique in X. From the definition, it is clear that the strict-EKR property is equivalent to the property St of 0, and we discuss the following recent results obtained by EP. As Q tends to infinity, where Q is a prime power, almost all Paizer-type graphs of type Q plus 1 over 2Q, that is, the number of slopes is a half of the total number of slopes. So almost all such Paizer-type graphs have the property St of square root of Q over 2. Theorem 7, as P tends to infinity where P is prime, almost all Paizer-type graphs of type the floor of 2P minus 2 over 3 P have the strict EKR property, and almost all Paizer-type graphs of type P plus 1 over 2P have the property St of P over 20. And one more theorem, let n be an integer greater or equal to 2 with the largest proper divisor being t, and let q equals p to the power of n. So p is prime. As p tends to infinity, almost all Paizer-type graphs of type q minus o of p to the power of tq do not have the strict EKR property. In lecture 4, we will discuss a recent result stating that the non-canonical cliques, when exist in the block graphs of orthogonal areas with parameters OA of square root of Q plus 1Q, obtained from the affine plane AG of 2Q, necessarily have the sub-array structure. So this does not solve the question by Gottswil and Marr in negative, but it just says that a counterexample does not arise from the affine plane HG to Q and from the corresponding orthogonal arrays, but an interesting project could arise from the investigation of the EKR properties of the block graphs of orthogonal arrays with parameters OA of square root of Q plus 1Q obtained from affine planes different from HG to Q. In particular, we plan to examine the database of small projective planes by Eric Moorhouse. Indeed, the deletion of a line from a projective plane together with its points results in an affine plane that depends on the choice of the deleted line. And this is a rich source of orthogonal arrays. And a counterexample might be there. And we have discussed the topic, the first family of graphs for which the notion of intersecting is well defined. So we can talk about canonical cliques, canonical intersecting sets that correspond to canonical cliques, and we can talk about Erdős-Ko-Rado properties. A second family of graphs I would like to discuss is related to designs, and let us recall some definitions. A 2NM1 design is a collection of M sets of an N set with the property that every pair from the N set is in exactly one set. A specific 2NM1 design is denoted by VB, where V is the N set, which we call the base set, and B is the collection of M sets. These are called blocks of the design. A 2NM1 design may also be called a 2 design, and a simple counting argument shows that the number of blocks in a 2NM1 design is the fraction with enumerator n multiplied by n minus 1 and the denominator m multiplied by m minus 1, and each element of V occurs in exactly n minus 1 over m minus 1 blocks. This is usually called the replication number. The blocks of The blocks of a 2 design are a set system, and every pair from the base set occurs in exactly one block. Thus, 2 distinct blocks of a 2 design must have intersection size 0 or 1. An intersecting set system from a 2 design is a set of blocks from the design in which any 2 have intersection of size exactly 1. A question that naturally arises: what is the largest possible such set? Clearly, if we take the collection of all blocks that contain a fixed element, we will have a system of size n-1 over m-1. An EKR type theorem for 2 designs would state that this is the largest possible set of intersecting blocks and determine the conditions when the only intersecting sets of blocks that of blocks that have this size is the set of all blocks that contain a fixed element. The only intersecting set of blocks that has this size is the set of all blocks that contain a fixed element. The first result would be the bound in the EKR theorem, and the second would be the characterization. The block graph of a 2NM1 design, VB, is the graph with the blocks of the design as the vertices in which 2 blocks are adjacent if and only if they intersect. In a 2 design, any 2 blocks that intersect meet in exactly one point. The block graph of a design VB is denoted by X indexed by the pair VB. Alternatively, we could define a graph on the same vertex set in which 2 vertices are adjacent if and only if the blocks do not intersect. This graph is simply the complement of the block graph. A clique in the block graph X with index VB, or a co-clique in its complement, is an intersecting set system for from the design VB. Fisher's inequality implies that the number of blocks in a 2 design is at least n. If equality holds, the design is said to be symmetric, and the block graph of a symmetric 2 design is the complete graph Kn. To avoid this trivial case, we assume that our designs are not symmetric. Let us discuss a well-known theorem. The block graph of a 2NM1 design that is not symmetric is strongly regular with the following parameters. The desired bound says that a clique in the block graph of to an M1 design has size at most n-1, choose m-1, it is not difficult to construct a clique of this size for any I from the set from 1 to n. Let Si be the collection of all blocks in the design that contain I. We call the cliques Si the canonical cliques of the block graph. From this, we know that a set of intersecting blocks in a 2 design is no larger than the set of all blocks that contain a common point. This is the bound for an EKR type theorem for the blocks in a design. It is not known for which designs the canonical intersecting sets are the only maximum intersecting sets. Gotzel and Marr offer a partial result in theorem 10. If a clique in the block graph of a 2 and M1 design does not consist of all the blocks that contain a given point, then its size is at most m squared minus m plus 1. Let us give a short proof. Assume that C is a non-canonical clique and that the set 1 so on M is in C. Divide the other vertices in the clique into M groups labeled GI such that each vertex in group GI contains the element I. Assume that G1 is the largest group. Since the clique is non-canonical, there is a vertex in GI for some I greater than 1. All the vertices in G1 must intersect this vertex, so each vertex of G1 must contain one of the m-1 elements in this vertex, but not the element I, as 1 and I are both in the set from 1 to m. Since no two vertices of G1 can contain the same element from the vertex in GI, the size of G1 can be no more than m-1. Since G1 is the largest group, the size of the clique is no more than m multiplied by m-1 and plus 1. And we are done. A corollary of this is an analog of the Erdős-Ko-Rado theorem with the characterization of maximum families for intersecting sets of blocks in a 2 and M1 design. Corollary 1. The only cliques of size n-1 over m-1 in the block graph X with index VB of a 2 and M1 design with the property that n is strictly greater than m cubed minus 2m squared plus 2m are the sets of blocks that contain a given point I in the set from 1 to n. The characterization in this corollary may fail if the opposite inequality holds, that is n is less or equal to m cubed minus 2 m squared plus 2m. For example, consider the projective geometry PG of 3, 2. The points of this geometry can be identified with the 15 non-zero vectors in a 4-dimensional vector space V over the field of 2 elements, and the lines can be identified with the 35 subspaces of dimension 2. This gives us a design with parameters 2, 15, 3, and 1, where each block consists of the 3 non-zero vectors in a 2-dimensional subspace. There are exactly 15 subspaces of V with dimension 3, and each such subspace contains exactly 7 points and exactly 7 lines, and so provides a copy of the projective plane of order 2. In the block graph, the 7 lines in any one of these projective planes forms form a clique of size 7. In addition, each point of the design lies in exactly 7 lines, and this provides a second family of 15 cliques of size 7. So the second family of cliques are canonical in this sense, and the first one are non-canonical. And the inequality from the corollary does not hold. We can say something about the equality case. Let me recall that in the equality case, the characterization may fail, but in case if we have the equality, a non-canonical clique in the block graph of such of a 2NM1 design necessarily forms a subdesign with parameters m squared minus m, m1, which is a projective plane of order m minus 1. And let us discuss some open problems for block graphs of 2 and m1 designs. Problem 6, determine a characterization of the 2 and m1 designs based only on the parameters of the design for which the only maximum cliques in the block graph are the canonical cliques. We have considered an example of a design with a block graph that with a block graph that has maximum cliques which are not canonical cliques. These maximum cliques have an interesting structure, namely they form a subdesign isomorphic to the Fana plane. It is not clear if this is a result of a wider phenomenon. Problem 7. When the block graph of a design has maximum cliques that are not canonical, are the non-canonical cliques isomorphic to smaller designs? And in general, it is interesting to determine all the maximum cliques in the block graph for any 2NM1 design. The stated problem suggests a comprehensive investigation of 2NM1 designs that N and M, such that N and M do not satisfy the inequality. Let us have a look at the known infinite families of two designs, equivalently Steiner systems S of Tmn, where T equals 2. For this, let us have a look at item 5.11 in Handbook of Combinatorial Designs, which provides the following 4 known infinite families of Steiner systems S of 2Mn. The first one is given by the lines in a projective space. The second one, points and lines in a projective space. The second family is given by points and lines in an affine space. I mean finite, projective and affine spaces. The third family has parameters 2q plus 1, q cubed plus 1, where q a prime power is a prime power, and family number 4 is known as Denniston designs. Its parameters depend on 2 values r and s, two integers, such that r is greater or equal to 2 and strictly less than s. For family 3, the inequality from the sufficient condition by Godswill and Marr, the inequality on N and M is never satisfied for not family 5, but for family 4, should be family 4, if S is, it can be easily computed that if S is strictly less than 2R, then the inequality is not satisfied. So both families 3 and 4 are non-trivial in the sense of EKR properties. What can we say about the first two families, projective and affine designs? Projective designs, if we consider projective designs on points and lines in projective space PG of DQ. If D is greater or equal to 4, the inequality is satisfied, and we have only canonical cliques in the block graph. If D equals 3, we have equality in this inequality, and the inequality is not satisfied. The inequality from the sufficient condition. The block graph in this case is the Grassmann graph JQ of 4, 2. The subgraph induced by the first neighborhood of a given vertex is Q clique extension of Q plus 1 times Q plus 1 lattice. A given vertex lies in Q plus 1 canonical cliques, say the rows of the extended lattice, and also in Q plus 1 non-canonical cliques, respectively the columns of the extended lattice. If D equals 2, the inequality does not hold, but the design we have is given by the lines in a projective plane, and the block graph is a clique, and we have nothing to do. For the second family, namely the family of affine designs on points and lines in the affine space HGDQ, if D is greater or equal to 3, the inequality is satisfied, and we have only canonical cliques in the block graph. If D equals 2, the inequality does not hold, but the design we have is given by the lines in an affine plane. The block graph is a complete multipartite graph, and all cliques are easy to describe. Thus, maximum cliques in the block graphs of projective and affine designs on points and lines are known. And let us complete this lecture with some concluding remarks. In this lecture, we have discussed extensions of the EKR theorem to two important classes of strong irregular graphs. The first is the block graphs of orthogonal arrays, including Paley graphs of square order, and second, the block graphs of 2 and M1 designs. We have also formulated open problems and discussed possible directions for investigation. In the next lecture, we will discuss some conjectures whose statements can be viewed as the Hilton-Milner theorem for Paley graphs of square order and special subclass of Bézier graphs. Thank you very much for your attention.
Oh, thank you very much for the nice, interesting lecture. Any questions to Sergey, please? Yeah, Akihira, yeah, sure.
Yeah, can you explain problem 1 again? I don't understand the what that that problem asks.
Find a characterization of the orthogonal arrays based only on the parameters of the array, for which all the maximum cliques in the orthogonal array graph are canonical cliques. So an orthogonal array has two parameters, M and N.
Yeah, and
if we have
inequality,
if we have this inequality, we know that all the maximum cliques are canonical. So this is sufficient condition, but it may be not necessary.
I see. So the problem asks when this hypothesis is not satisfied, then the conclusion always fail, or it's possible to give some characterization. I see. So there's analogous problem for the Steiner 2 design, right?
Yeah, right.
I think you mentioned. Yeah. Okay. Yeah. Thank you very much.
Okay, I also would like to ask you about problem number 5. I mean, oh yeah, right, yeah. So you said that it was possible for you to solve problem 4 just partially. And
Problem 4 is solved completely in a more general statement.
In more, yeah, right, yeah. But problem 5 says that there are some open questions still there, right? Yeah.
Yeah.
So I mean, what are the main difficulties in showing this statement, problem 5?
These two problems are formulated in the language of vector spaces. So Gotzel and Marr in their book suggest algebraic approaches to Erdős-Ko-Rado theorem. This means that they try to reduce Erdős-Ko-Rado problems. I mean, they would like to formulate Erdős-Ko-Rado theorems and try to try to prove them in terms of some algebraic notions. And in the case of Paley graph of square order, despite the proof by Blokhuis is already known for many years, they suggest an alternative approach to this theorem. And this alternative approach involves vectors, the vector spaces and the balanced characteristic vectors of sets of size q. So I think this problem is doable, but some clever way to manipulate the corresponding vector spaces is needed.
Right, yeah, I see.
Sergey?
Yeah.
Hello?
Yeah.
You said the problem 4 is completely, problem 4 is solved?
Yes, it was recently solved. So yeah. Just after the problem 4, so the link, the reference is given in the abstract, but this paper was published by Shamil Asgarli, me, Hui Qilin, and Chiho Ip in 2022. So
but it says that it is only equivalent to some other property, but then you prove that some other property is true.
We prove directly for all block graphs of orthogonal arrays that the balanced characteristic vectors of canonical cliques span the corresponding eigenspace. So we didn't consider Paley graphs in a particular way. So we solved this problem in a more general way. Yeah.
I see. Yeah, I see. So yeah, I misunderstood the sentence that you wrote. You did this, but this was not clear.
Sorry. I agree. It's not clearly written.
Yeah, thank you for clarification.
Yes, thank you. Yeah. Any other questions to Sergey? Well, if not, then let us end again. Thank you very much. It was very interesting and a lot of open problems. So interesting topic. I hope that we will see you and all other participants almost in 1 month. So the next lecture will be on May 23rd. So good luck and see you.